today, but we're going to do kind of the same thing as limiting reactants. So if you happen to be not here, obviously you probably should still do these. There's some lessons over there for you, anything that you've missed. And if you can't find them over there, then let me know. But lessons are over there if you missed anything. And like I said, some of you guys might be behind a little bit, so it's probably important that you guys catch up here. Still important that you probably do those. We're going to do something similar today. And I know it's been a while, so we'll kind of take it somewhat slow, I guess, but we're going to do kind of similar things today here. So today we're going to talk a little bit about gas stoichiometry. We've talked about mass stoichiometry, so moving n around, finding out the mass. Today we're going to move n around again, of course. To move n around, we're going to use the ideal gas law, because if you remember, the ideal gas law here has amount, or n in the formula, so we can use that to move around, or to use that to find out the pressure, or the volume, or the temperature, for example. A couple things about this, of course. Remember, pressure has to be in kPa, volume has to be in liters. This, of course, is moles. This is your universal gas constant, 8.314, and this is your temperature, and it has to be in Kelvin. So don't forget that, of course. Okay, this is going to be your Unit 2 review kind of thing for a little bit anyway, for some of it. But basically it's, you know, a lot of focus on PV equals nRT, ideal gas law. Okay? So let's take a look at the first example here. Like I said, there's all the units that you need there. During combustion reaction, we're going to take 25 grams of propane and we're going to burn it in a 75-liter steel tank. So once again, as always, you want to write out a chemical equation for this. Propane, I don't expect you to know that, but it is this here. I would tell you that, of course, unless I forget. But propane, C3H8, okay? Combustion reaction plus O2. We have a fuel here, so don't forget anything in my fuel. Carbon gives me carbon dioxide, of course. Hydrogen gives me H2O gas, of course. Okay? We're going to balance it, of course. 3 carbons, so let's put 3 carbons here. We got 8 hydrogens, so let me put a 4 there, for 4 times 2 is 8 hydrogens. And on the right-hand side, I got 6 and 4, so 10 oxygens. And on this side here, I need 10 oxygens as well. That's weird. Hey? All right, well, whatever. Just the aliens, it's fine. Hey? There, see? Done. Okay, so 25 grams of propane. You're going to need to obviously make sure, guys, hey, we need to make sure we put this in the right spot. 25 grams of propane, so we're going to put that here. Is burned in a 75-liter steel tank. Where do you want to put 75 liters? Well, we're going to burn this all in a 75-liter tank. We could put that anywhere we want. We could put it underneath here, 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 or here. I think we're just going to leave it for now, and we'll kind of see where we need to put it for right now. At the end of the reaction, the internal temperature of the tank is 275 degrees Celsius. Calculate the pressure of the carbon dioxide gas. Okay, so today we're looking, well, in this particular example, we're looking for the pressure of the carbon dioxide gas. To find the pressure, what's the formula I need to use? Well, the only formula I know that does pressure, okay, is either P1 V1 T1 equals P2 V2 T2, right? Combined gas law, or PV equals nRT. And of course, that one makes a lot more sense because we have amount for that. Okay, and we can start filling in some things right away, of course. Let's see here, 75-liter steel tank, so let's put that here. We got 8.314 for R. The temperature is 275 degrees Celsius. Don't forget, we need to change that to Kelvin. So 548.15 Kelvin. Okay? We need to find the pressure. Well, to find the pressure, of course, what am I going to need to use? Well, if I want to find P here, I need to know V and RT. I don't know N, but I do know that for every 1 mole I burn here, I get 3 moles of product, right? 3 moles of carbon dioxide. So it's a 1-to-3 ratio. Well, I can use the molar mass here. Propane, C3H8, so 3 carbons, 8 hydrogens, that's 44.11, I believe. and I can find N from that. Okay? So 0.5667 moles. And remember, for every 1 mole that I burn, I get 3 moles of carbon dioxide. Well, I'm burning 0.5667 moles. So I would get times 3, right? 1.700 moles. And now I know nRT and V, and I can find P. Of course, to do that, you're going to take nRT, N times R times T, divided by V, right? So PV equals nRT. If I want to find P, nRT over V, yes? Okay, so let's do that. N times R times T divided by V. And I will get, all said and done, 3 significant digits. If you look back up in the question, so 103 kilopascals. Okay, so 3 significant digits in the question above. If you look back through all the example there, so 3 for my answer, yeah? Okay, good? Yes? Now, once again, is this a limiting reactant question? And the answer is, well, yes and no. Do you have to compare 2 things? The answer is no. You don't have to compare 2 things in this question. So if you remember to the Thursday before the break, we had to compare things. We don't have that here. We have lots of oxygen probably. They don't tell us anything specific about how much oxygen we have, so that would be what we call the excess one. They do tell me specifically that I only have 25 grams of propane to burn. Okay, so by default, this is kind of a limiting reactant question. It's not, it's not as tough as the other ones, of course, because we don't have anything to compare it to. We're going to do that in the next one here. But technically, that tells you how much product you're forming, yes? Okay, so you'll see what I'm talking about on the next one here, if you remember back to that. Any questions on this one so far? Questions, anyone? Okay, let's look at the next example here. Let's get you guys to write out the equation for this one here. This is always fun and entertaining. Zinc is placed into some hydrochloric acid, and what volume of gas is going to be produced. So I'll let you guys go ahead and write out the equation for that. Put the information in the right spot underneath each one. Okay. Okay, zinc and hydrochloric acid gives you single replacement reaction. Okay, guys, quiet. Shh. Single replacement reaction. So the zinc and the hydrogen need to switch places, right? So hydrogen, which comes in 2s, and of course, some zinc chloride, aqueous. Balancing. There you go. Okay. So put the information in the right spot. 15 grams. And what do we got? 25 grams. Molar masses we can find. Let's see, 65.41 grams per mole, I believe, and 36.46 grams per mole. And we can find N for these. Now, once again, okay, if we actually looked at this reaction here, we know that 1 mole of zinc, right, 1 mole of this reacts with 2 moles of this. So this is a 1-to-2 ratio. If we had a 1-to-2 ratio, it would give me perfectly 1 mole of this and 1 mole of that. The question becomes, do we have a 1-to-2 ratio here of moles? Okay, so we need to figure this out here. Let's see, 15 divided by 65.41, which is about 0.229 moles, and 25 divided by 36.46 is about 0.685 moles. Is that a 1-to-2 ratio for the moles there? Well, if it was, look, if this is let's even round this here. Let's say this was 0.23 moles here. If this was 0.23, I would need twice as much, right, to react with it. 1-to-2, is this a 1-to-2? It's not, right? If this is 0.23, this would have to be about 0.46, yes? And look, it's 0.68, so I have lots of this stuff here, yeah? Remember, if you're not sure, what do? Okay, and I would recommend doing this all the time. You say, hey, look, this is for 1 mole here. That's what I figured, 0.229. But this is for 2. Let's divide by 2 and get it down to a 1-to-1 ratio, right? So if I take this here and divide by 2, because there's a 2 out in front, 0.685 divided by 2 is 0.3428 moles. Now, if this reaction did, in fact, react in a 1-to-1, okay, those are the numbers I would have there in a 1-to-1 relationship. So 1-to-1 relationship, it looks like to me that the zinc has only got 0.229. We have 0.3428 for the hydrogen chloride. We have more than what we need for hydrogen chloride. So this is your limiting reactant here, right? You take the less of the two, and you're going to move it over to here, okay? Remember, the one that runs out first is your limiting reactant. It's the one with the least amount of moles when you get it to a 1-to-1 relationship. It determines how much product you can make, right? In this case, it says the resulting gas is released into the air at standard pressure. This is my gas, that's a solution. So this is my gas here, standard pressure, and a temperature of 21.3. Nope, let's try that again. 294.45 Kelvin, okay? So, once again, we know R, 8.314. Volume, don't know the volume. In fact, it says what's the volume of gas produced, so that's what we're looking for. What's the volume of gas produced? If I could find N, I would have nRT and P, and I could find V, okay? N, this is for 1 here, 0.229, move that over to here. That's also for 1, so 0.229 should go over here as well. And of course, you want to use the unrounded number. So is it 0.229? No, it's 0.229 something, 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 right? If you don't have that on your calculator, maybe you need to get that back on by doing this division here again. 15 divided by 65.41, nope, 15 divided by 65.41, 0.229322735, okay, is the number you want to use there. We're going to take N times R times T, and we're going to divide it by 101.325, and we get 5.54 liters as your final answer, 3 significant digits again. Okay? Questions on that, anyone? We're going to do one more here. Any questions? When you compare them, right, we want to make sure we're comparing them. The easiest thing to do is, if you can look at this and determine which one the limiting reactant is, that's fine. If you can't, because sometimes they're going to be really close, then divide this one by 1, which of course gives you the same thing, right, because there's a 1 out front. Divide this one by 2, because there's a 2 out front. Then you have it down to a 1-to-1 comparison. You take the smaller of the numbers and move them over accordingly. Now I took this one, okay, over to here. That's a 1-to-1, so I don't have to worry about multiplying it by anything, but if I did, I'll show you an example in the next one, I think. You'll see that we have to multiply, okay? Any questions, anyone? Let's do one more. Once again, I'll get you guys to do the equation for this here, balance it. Put the information in the right spot. Notice you have here megapascals, megapascals. So hopefully you remember what that is as a kilopascal. Yes? No. Oh boy. Megapascal is how many kilopascals? 1,000, yes? Times it by 1,000, yes. Okay? So, now as you guys record the information. Okay, so hydrogen gas plus oxygen gas gives you water vapor, aka water gas. Balancing, you'll need a 2 there and a 2 there. Okay? Obviously, most of you guys did that okay. Make sure you put the information in the right spot here. So let's write down all the stuff we know. We got 30 liters of hydrogen gas at 15.5 or 15,500 kilopascals. Let's see. Looks to me like makes most sense probably to talk about PV and RT there because we already have the pressure and the volume, right? So R, we know, is 8.314. And the temperature, they tell us actually the temperature there too, so that's probably a good idea here. 17.5 and 273.15, we give 290.65. Okay. We're going to mix that with 20 liters of oxygen, 12.8 kilopascals, so 12,800 kPa. Let's see, R is 8.314. Temperature is 22.4, so let's see. 273.15 and 22.4, 295.55 Kelvin. Okay? It says what mass of water vapor, what mass of this is going to be produced by this reaction? Well, when you look at this here, the question should always be, you know, can I find N for both of my reactants here? And if I can I find N for both? If you can, you have to consider which one's going to run out first. Now, if you look at this equation here, it says that 2 moles of hydrogen should react with 1 mole of oxygen, right? I guess the question is, how many moles do I have of each one of these? Is it in a 2-to-1 ratio? Probably not. Which one's going to run out first? So that's what we need to find here. To find N, of course, a little bit of review here for you. You're going to take PV over RT. Yes? Okay? Solving for N. So PV, let's see, 15.5 times 30 divided by 8.314 and 290.65. Now, if you don't use brackets, you're going to get some kind of crazy number here. You should get about 192 moles roughly. Okay? Once again, I'm just going to get rid of this for a second here. This is a limiting reactant question. How do I know? Because I can find N for both reactants. Okay? If that's the case, look, 192, but that's for 2 here. So I'm going to divide by 2 and find out what's N going to be just for 1, because I'm going to have to compare these two numbers here. Works out to be about 96.21 moles. Okay? And that's for 1. Okay, let's go over to the other side here. This is already for 1 here, so whatever I get is going to be what I get, right? It's going to be N, it's going to be for 1. I can do a quick comparison of the two. So 12,800 times 20 divided by brackets. Don't forget brackets on this one. 295.55, and I get 104.1835 moles. And once again, if I'm going to, well, look, it's ready for 1, yes. So if I divide by 1, I'm going to get the same number. I basically have 104 moles here. Okay? We look at these two and we compare them, that one and that one. Which one do I have less of? Well, it appears to me that we have less of the hydrogen, yes? We only have 96 moles. So this is your LR, limiting reactant, yes? We need to put that up there, please. And that, once the hydrogen runs out, this reaction is going to stop. Look, when I've used up all my hydrogen, am I going to be able to make H2O? Hydrogen's done, right? So you're not going to be able to make any more water. Water needs hydrogen. So we're going to take this and move it over to here. Because the limiting reactant always determines how much product we can make. Okay? Once it runs out, we're done. We stop. So I need to get it over to there. But remember, this is for 1 here. So if I'm going to take this number here, I need to multiply it by 2 to get over to there. Yes? Okay? If you want to take this number here, which is already for 2, remember this was the 2 before, you can simply move it right over there for 1 times 1. Because this is a 2 to 2 ratio. So if you take this number here, that's already for 2 moles. That's for 2 moles there. If you're going to take this bottom one, you need to multiply it back by 2 again. Okay. Either way, you're going to end up with 192 point, whatever that number was here, 4299227. And remember, you have to use the unrounded number. Okay. Molar mass of water, 18.02 grams per mole. Multiply those two together, 18.02. Oops. Let's see, 192.4299227. 3,467.587 grams. Okay. And then we're going to have to do some significant digits. All right. Significant digits, there's 3 for the limiting reactant here. So 3 in my answer. 3 in my answer would look like this. All said and done. Okay. Any questions on that one? Yes, no? Questions? I got a few more things to show you here, but any questions on that? Ask. Yes, no? Okay. All right. Well, if you look at your, let's look at your homework for today. It should be on the back there, stapled on there for you, or whatever, your last page there. The very first question is going to say something like this here. I'll kind of help you out just with the first one here real quick. What mass of sulfur dioxide gas must be decomposed in order to produce 13 liters of oxygen at 18.5 and 13.7 psi? So what mass of sulfur dioxide gas has to be decomposed? Sulfur and oxygen, yes? Okay. So we have to remember our 5 types of reactions that we have from before, right? Decomposition, simple decomposition, formation, combustion, single, double, replacement, yes? Balancing, you'll have to put an 8 here, of course, and an 8 here. All right? Now, that's pretty much what I'm going to tell you for that part there. It says, what mass of sulfur dioxide has to be decomposed? So you're going to look for that. But listen, if you look through the numbers here, look through the question, look through the numbers. Number 1, okay? You got 13 liters oxygen at 8.5 degrees Celsius and 13.78 psi. Well, you can't use psi with this formula here, PV equals nRT, right? So you're going to have to convert psi, yes? This is Unit 2 review stuff. So how do you convert it? Well, you look on the back of your periodic table. You say 14.7 psi on the back of the periodic table is the same as 101.325 kPa. I have 13.78 psi. How many kPa is that? Remember that? Okay. So that's been a while, obviously, but that's what you need to do. Some of you guys set it up a little differently. That's fine, whatever, but that's basically what you're looking at there. And if you do that, I forget exactly what you get, but it's about, I think it's about 94.9 kPa, roughly. And of course, you're going to want to do that because you need to use the unrounded number, okay? So it's about 94.9-ish kPa. So you're going to have to do that, okay? Now you can use this, right? Because now you have that in kPa, all right? So I'll let you work on the rest of that on your own, but that's number 1, okay? So we can't forget about the units to go with these. Kilopascals, liters, Kelvin, R is 8.314, N is moles, of course. And we may have to do some conversions from before, okay? I'm going to give you guys the answers for these as well. So if you guys are done with this, I'll give you guys the answers, yeah? Okay. So answers for the worksheet here are going to be, let's see, 32.6 grams. Number 2, 157 liters. Number 3, 39.4 liters. number 4, let's see here. All right, and I'll also tell you for number 9 here, or sorry, for number 7. Number 7, ammonia is an H3, okay, which I don't know if we remember that or not, but it's NH3, ammonia. Okay, in case you need that. So there's your answers there. I'll let you guys get to work on those. If you have any questions, let me know. Probably be able to get this done this period, I'd imagine. So if you have any questions, like I said, bring up your information, bring up your sheet, balanced chemical equation, etc., and I'll help you out. Okay?